PowerPoint. Yay.
There we go.
Yes, Microsoft doesn't leave me today. Okay, good. Thank you, everyone, for staying and bearing with me to this session. Well, you've heard about myself. I've introduced myself earlier, but I need to say that I'm really passionate about Kubernetes, and today's talk is like a joint adventure of things experienced with Kubernetes and also with some other programming languages. I hope you'll enjoy it. And let's dive into the actual important stuff for today. So in the slide, you have the definition of the anti-patterns. But what are actually anti-patterns are patterns that started to be used with a good purpose. So we wanted to use these kind of patterns. We wanted to use good patterns, the ones that we know in the literature, to apply them in the real life. But down the road, something went wrong, and that became an anti-pattern. And why talk about anti-patterns in this talk today? Well, because it's good to also know what it can go wrong by following a certain pattern and to see what remedies are there for it. And the second aspect of my talk's title was about system stability, right? So stability of a system, actually robustness of a system, is defined for the fact that regardless of what happens with your system in terms of disruptions, the system continues, the system can let users to continue their work. So it's pretty much letting the users do their work, even though that your application is not loading as fast as it used to be, or your functions in your application are not going as well as they should have gone. So these disruptions can occur, and this is what you should take in mind when you're thinking of stability of a system. Not always the happy path, but also have in mind that your system might not perform that well, and it should be like almost good for the user experience. First of the anti-pattern that I want to bring to your attention is one about application deployments in a specific order. There's nothing wrong of planning and thinking about deploying your system, especially in case of a distributed one, to make it in a specific order. Also, back in the days when I started developing, there used to be people that were dedicated to doing actual deployments, some manual. And in those cases, well, you would have instructed that person how to do the things, or he or she would have had a set of instructions and would have done it in a specific order so that your application will end up available to your users. And some of these people evolved and improved their skills, or we have improved our skills, but we are coming with the idea of doing things in a specific order, even from when learning programming. We learn things iteratively, to be honest. And I want to bring to your attention a sample of such a deployment. So every time that we are thinking of a distributed application, we're thinking of microservices, a lot of applications that do their own thing independently. But in the end, they have to make for a user a front end and a back end. So let's just say that we have just two microservices in this case, one with front end, one with back end. And when you're thinking of deploying them, coming from background of a developer, you're thinking, yes, but my front end cannot function without the back end, right? Because I can serve to the user a beautiful interface, but I still need some data. So in your mind, you're starting thinking, I should be having the deployment of the back end before my front end is starting. And a schema such as this one described here arrives in your mind, and you start looking into doing the deployments like this. And you're actually using an orchestrator in this case. So this case here, it describes using an orchestrator and using Kubernetes and making use of readiness probes to make sure that your system is available. So everything starts with the backend deployment. At the readiness probe checking, you're checking that if your application is ready to receive traffic. If yes, then if your backend is ready to receive traffic or to provide traffic to the front end, then go ahead and go with the front-end deployment and do your part there. If not, you can go ahead and restart your service and try again to put that up and running. And you see here something called crash when the liveness probes give up. So you can end up also in the failure state. And this is what is coming really interesting. So on the happy path, you have an application up and running, ready to serve requests, all good with this kind of a deployment schema. But Having things in a specific order to start and stop processes is not necessarily good, because you're putting a dependency on successfully deploying something else. Also, a service is waiting to start by depending on the availability of another component. And by the way, the condition you saw earlier for the front end to start when the backend is becoming available can be easily translated with a simple command of wait in Kubernetes. So that's pretty much the trick behind it. Why is it that bad? Well, first of all, the wait time between deployments equals application not fully functional, because let's face it, even the tiniest moments that you are waiting between deployment, I'm actually making ready the deployment for backend, that tiny moment means application not fully functional for your users, because you're not making your front end available for your users as well. And when the condition is never met, the next deployment cannot proceed and the process breaks. So this is what you call like a whole pipeline for a certain feature broke because, well, we had a dependency on something. What are the solutions for these kind of situations? Well, one of the solutions is concurrently deploy and start all parts of the application. That's the same thing to do. Plus, use the retry patterns. So the readiness probes are themselves making leverage of these retry patterns. I mean, liveness probe has its own parameters to make you retry and reassess the state of your application. Maybe it didn't start it in the given time because of certain dependencies inside of it that were not ready to serve traffic and to do their work, but you can try again a little bit later and see if everything's up and running. And last but not least, use circuit breaker patterns. This all sounds nice, but I think right now you're thinking, okay, so you're telling me that you want to throw everything and deploy everything at once, but I still need my backend to serve something to my front end. So how can I make it happen to avoid that situation when things break due to an unsuccessful deployment of a part of my system? Or how can I leverage the part of like not having any downtime? Well, there are deployment strategies available. Kubernetes comes with two built-in, the recreate and the rollout strategy. But what you should think of on the long term when your application matures is to have deployments which are a little bit more complex and ensure you that you don't have run any downtime through their design. One of those being blue-green deployments for their instant rollback feature. Now, blue-green deployments, what they actually consist is like, for example, you have your own application that has 2 pods, but pod version 2, for example. And then this is your blue app. It's up and running and working. Now you want to make a deployment with the version 3. So what you're actually doing, you are making a deployment of the version 3, and you're waiting until version 3 becomes ready and available to start serve traffic. And then you are switching the traffic from version 2 to version 3, making the traffic going only to the version 3. So in this state, you are making sure that your version 3 is actually up and running before actually switching the traffic, so their user doesn't feel any loss in terms of their data or their functionalities in the application. And last but not least, you totally disconnect the version that you don't like anymore, and that's it. If something fails, for example, with version 3 on deployment or when spawning it up, then you can always go back with version 2, or your users actually stay on version 2 and they're not affected when they're using your application. Now, another way of thinking of a deployment strategy is using canary deployments. The so-called canary deployments are where the user does the testing. So in the situations when you have features that you want to see how your users are reacting to, or for example, you can do these situations for UATs. So not necessarily go with this on production, but when you're doing UAT sessions and you want to see how's the acceptance of that set of users that does UAT for you, you can use canary deployments. And in canary deployments, what you're doing, you're kind of redirecting like 1% of your traffic or a small amount of your traffic to the new version you want to spawn. And you're having this version 4 running in parallel with your version 3. So you are putting all this to your users, but only a small percentage of it gets the new version and can do the testing and can report back to you if you have any issues, while the majority of your users are not impacted. This is a great feature when you are not necessarily uncertain on what you want to release, or if a certain UI, for example, is going to be as catchy as the previous one was, and you want to test some reactions from your users. And last but not least, if you're happy with version 4, you can make it available for everyone slowly. So this is a way like when you're putting your users to use the hard work for you. But on the other hand, it's another way to have a safe deployment strategy and make sure that even though that you're concurrently doing things and you're concurrently deploying your application, you're not losing any of the requests, and you're still serving something to your users. The next anti-pattern that I want to bring to your attention, again, spawned from the good intentions of making good distributed services in cloud-native applications, is the one regarding the integration, communication, and composition. And how is this one occurring? Well, you have a new shiny distributed system that, well, let's say you've built with microservices, has the best and newest technology on the market. But what happens with the system when it has to integrate with an application that is legacy? That it doesn't work all the time, and it also has some timings when it stops, and thus your own system gets to stop. Secondly, a lot of developers nowadays think of containerizing everything and putting everything in Kubernetes without assessing the impact of their decision. And why are they doing that? Simply for the reason of thinking like maybe it's good to have the same network and share the same network features, and maybe there will be no loss of data because they're in the same place. Not necessarily. Some things are not meant to be containerized, to be very honest. And of course, the distorted usage of declarative deployment pattern, like when you are thinking that everything can be deployed with the deployment resource in Kubernetes, for example, and you don't look at the qualities of your application, that might not be as stateless as you're thinking, and it impacts the overall application functionality that you are going to have there. Why is it bad to look into intercommunicating synchronously the systems? Well, first of all, when you're integrating, by the way, with a system that you don't know how it's going to behave in time and is not your responsibility, you can get into the situations where HTTP requests are being sent, but you don't necessarily receive a reply. Like the system that is getting the request, it gets it, but it doesn't react in any way because, I don't know, something changed in processing the data and you're not made aware of that. And you can end up, of course, in like all the time waiting for the response and thinking, why I'm not getting anything. Then there are situations when the provider of the service that you are integrating with is giving you the response in a different format or has a different structure. It happens. So because you're not in the same team necessarily with the applications that you're integrating with. You are the consumers of those. It can happen for those teams to change their APIs. They can leave the request the same, but they can change the structure of the response, and that's very fun. And you can end up with the fact that on your side, you don't know how to process that response properly, and you are getting into issues with your own application. And of course, your user see that, well, your application is the one who's not behaving correctly. Also, that you should know that synchronous calls are amplifiers of failures and blockages. So all the time thinking of the systems in the distributive new world to make asynchronous calls and not necessarily synchronous one. We're starting as developers thinking that everything that has a request has a response, and everything is command-based and we have a kind of a difficulty to think a little bit to the asynchronous part. But in the end, we should know about this, that they can facilitate failures for us. Then tightly coupled middleware, the one that has been containerized and put in Kubernetes, for example. The fact that you containerized it, it doesn't mean you make it better. It means that you move something that used to be in a place inside of your orchestrator and not necessarily helping you on the long term. What the solutions are there for preventing failures when you're doing integrations? First of all is the circuit breaker pattern. There's a lot of literature on this. I'm not going to insist on it. What you should know on the circuit breaker pattern is that you should always consider delayed retries. A lot of developers, when they see the implementation of it, they think of like, okay, so the caller doesn't respond to me, then I'm going to the fallback method. The user gets some kind of a message there, like, please try again later. And that's it. That's the end of the story. No, the idea is that you have served the user something to calm down the user for the moment when you cannot serve him the real thing. But you need to think of retrying his request and sending the user the real data. And secondly, you should always record, and correlate the state changes that occur with your application, even that you are, implementing correctly a circuit breaker pattern, because situations when you need to open the circuit and you have to make sure that any failure is not being propagated further are good to be monitored and to be reviewed later to see if there's a pattern between those situations of error. A sample of application level solution is present in the slide. I told you I'm a Java developer still. So I chose the Spring Boot with Resilience for J example. A few things that you are having in your mind when you're using circuit breaker pattern with, I think, anything at the application level is you have to provide a sliding window, meaning a time frame when you are going to leave your circuit in the open state. How much time you should wait for that sliding window to be opened. And of course, the allowed number of calls in the half open state, if that is something that the framework is providing. And of course, how much failure would you like to permit to your system? These are just a few things because the actual Resilience for J configuration very thoroughly is very long. But just to respond to you, this is what you can do at the application level. And there comes a question like, is this enough? Because a lot of developers, or from the developer's point of view, the one that's writing the application in Java, for example, you can say that this is enough. I've done it. I've implemented the circuit breaker pattern. My integration should now work and everything's fine, right? The thing is that, yes, this is fine. If your fallback method is retrieving a unified satisfying response. So for example, if your system that you're actually integrating with is not responding to you for a long time and your users get that please try again later response for a long time, maybe in the beginning that's satisfying for them, but on the long term, that's not very satisfying. So for example, consider booking a vacation. You don't want to see booking a vacation, please try again later for a long time. You want to see an actual response and interaction that your request was received. So this brings you to the part where, is your end user happy that the real data is not present in the response? Most of the time, your end users will not be happy with not having some real data and having like a message or something default. And the funny thing is that most of the time when you're integrating yourselves with these kind of systems that provide you data, real data, they give you meaningful information for you, such as prices or rates for booking a vacation, for example. And you really need that. You cannot give to the people a default price, for example, for a vacation. There's little chance that you could find a satisfying price for anything. Some transition solutions are needed. So considering only the application level state of circuit breaker pattern might calm the things for certain cases, but not all the time. So there's the idea of implementing a two-layer cache solution. Now, this is my personal opinion. you can challenge me afterwards. Implementing a cache-based solution is very good, and you can do it by determining first the outage pattern. So you can determine the outage pattern of the service that you're integrating with or the application that you're integrating with. And based on that, you can think of how you're designing your two-layer cache solution. You can determine the outage pattern, by the way, by hammering and stress testing and load testing the service that is doing all the bad stuff for your application. That's one way. On the other hand, there are some very old, nice legacy applications that have very nice people that are maintaining those. And they send you emails and they say, hey, dear user, we're going to be out of our normal functionality for 2 hours, 3 hours. Yeah, basically, most of the time they're affected in our time for some kind of maintenance. So you can design your cache solution based on their maintenance windows as well. Now, this is, I think, the best case ever to know the maintenance window and to tailor your cache solution based on that. But most of the time, stress testing and load testing can give you the outage pattern, and you'll see how that is replicating. Now, looking at cache solution. Now, my example, I think that a key value-based database like Redis helps you a lot. So, for example, you can easily throw a Redis there and integrate it with your very nice written application that already is doing the circuit breaker pattern for the cases when things are not going really nice. But since you need to give some real data, you add also on top of it the caching solution. And in this case, when you're implementing this kind of a cache, of course, you have two options. You have the option to have it like a cache hit or a cache miss. So as obvious, when there's a cache hit, and I said that there's a two-layer cache. First of all, you check if the time to leave of the first layer cache has expired for that key that you're searching for. So you want to make sure that your key is actually, fresh and giving you good data. If the time to leave of that key has not expired yet, meaning the key is fresh, and I mean the value that key has associated is fresh, you can give it back to your users and you return the response from Redis. You're done. Now, if the key has the time to leave expired, you go to the second layer cache and find the entry. So at the second layer, you're kind of like doubting that you get the fresh key. So you're trying to call the real method, and on success, you're storing the new value on the key, and you put the new time to leave. So this is a happy case. And on failure, of course, because you need to retrieve to the user something, and your system, the calling system, might be not available, you can make the assumption that, well, the old key that expired, has time to leave expired, actually might be good of something since the other system is not available. So you can extend the existing time to leave to put it back in the first layer and return the result to the user. In the bad case that you're having a cache miss, meaning you're searching for a key that is not existing in your caching solution, you can always try to call the real method because you have no other option for it than try to call the real method and get the key. On success, yay, you are storing the new result with the proper time to leave on the first layer cache. But on failure, you will have to return a result covering the miss, meaning you'll still have to return that please try again later message, or a message that will calm down the user until he or she retries again. The adding on top of the other solution, the transition solution of caching, is narrowing down the unsatisfied user count. And you kind of have the ability to retain at least certain users based on what you're having in your cache pool. Wow, there's been quite a struggle so far, but I want to bring a little more to the circuit breaker pattern, and to tell you how we can even elevate this even further at the infrastructure level, meaning using a solution at Kubernetes level. So one way to do a circuit breaker pattern and to ensure that you are kind of guarded from all over the places is to use, for example, the implementation that Traffic has. It has its own circuit breaker pattern based on expressions. and can help you even more in handling failures, even from the infrastructure point of view. So you're not making even calls to your real service, you're just being stopped, and yeah, this is not available. You have to find a way to deal it at application and then transition level of your service. Now, traffic has a small downside, the fact that you cannot parameterize its fallback method. It's always going to retrieve to you a 503. But based on that 503, you can always rely that, okay, it's a 503, I have to find a way to call my users in to tell them that, well, something is not working properly. A very more advanced solution, also at Kubernetes level, is to leverage circuit breaker pattern with Istio. Now, this comes with a little bit of overhead because the destination rules of Istio means, of course, firstly, install Istio, put it on top of your Kubernetes installation. You have to have some training in using it, but you get more fine-tuning that you would have got with traffic. And you can even more customize, from infrastructure point of view, your calls and how your system is behaving even before reaching inside your application. So those being said, you kind of have an equipment to stop failures at every layer, not just at your application level, and you can narrow down the satisfaction level when you have to handle integrations. The next pattern that I want to bring to your attention, or anti-pattern, is the mirage of unlimited resources. And there was a question that I received like a few weeks ago. Somebody asked me, hey, how many resources can I put into a Kubernetes node? And the answer is, well, it depends how you configured that. On the example that you find on the internet, and also in the examples that are shared by even in official documentations, you will see that most of the time is being captured the essential information regarding that specific scenario. And a lot of people go ahead and they just get those examples and they put into practice. Such as an example, and this is my own example, so if anyone wants to blame somebody, it's my own, it's got from my own stuff, is creating a deployment resource like this. You know, there's nothing wrong with it. Kubernetes accepts it, it's going to process it, it's going to make a deployment with it. The thing is that it's missing a few things for the real life. It's missing the part when it has some resources associated to it. So a lot of developers and DevOps persons, not sure if DevOps necessarily, but a lot of persons that are starting with Kubernetes, they're thinking that they don't have to configure the resources part, that this is going to be automatically be supplied by the orchestrator, which it is, and everything is fine and everything is going on smoothly and perfectly for their system. It's Kubernetes, it's self-healing, it's minding its own business, it does everything for you, right? But there's a downside of not specifying these tiny resources and the requests and the limits there. The first one is that because you're not setting any memory or CPU when you're doing that kind of a blind deployment, like in my first example, is that this can result into scheduling an unlimited number of pods on your node, because your scheduler, your Kubernetes scheduler, sees that deployment and it doesn't have any limit to stop scheduling it. You didn't allocate any resources, so you can go ahead and do that unlimitedly, go wild. Also, their container could use everything that finds available on a node, if it's a high-consuming container, and it can invoke the out-of-memory killer. If you want, you can design. I've done it once just to prove myself that I, some theories of mine. I've built a container that was consuming a lot of resources and deployed it without any limits or any requests there. And of course, it triggered the out-of-memory killer, and yeah. It was an interesting experience, but I've done it on my local, so didn't affect others. But you should be aware of this, that it could use all the available memory on your node. And last but not least, by not specifying requests and limits, your containers can use the default memory limit of the namespace. The one that one could be assigned to your container. So that's not that's not a very nice thing. So to use everything that's available in namespace, and when you're going to try to schedule another resource, you're going to be, oops, they don't have anything else left. What solutions are there, actually? One of those, well, obviously setting the memory and CPU requests below their limits in the declarative descriptor files, or afterwards by editing the actual deployment you've done there. Another thing that you should think about is like control the limits of those resources via objects like resource quotas and limit range, and apply those namespace settings. So make sure that your namespace is not consuming more than it should from your node's capacity, and ensure that you are having a good economy in your node and in your namespace with all of your resources, regardless if you're putting or not the memory in the CPU requests. But the good practice would be to combine those two. And last but not least, because some of you might be wondering, hey, and how much memory do I put there? How much CPU should I configure there? So for example, for the CPU requests, you can keep it at 1 core or below. And if some of you are thinking, but what if my applications consume more? Well, this is why replica sets were invented, to help you to scale out what your application load is doing. So if you think that you will need more within your application, you can always leverage scaling and auto-scaling in order to help you unify and bring a good response to your users. Do not try to allocate more CPU and more memory thinking like, yeah, let's be there for the times when things are not going to be that good and there's going to be much more demand for my application. And since we're talking about scaling, another anti-pattern, and the last one for today, is one regarding scaling results. And in scaling results, the examples and the symptoms are pretty easy and can happen even in distributive systems. Like you can end up in scaling a lot one of your systems that has, like, for example, in this case, 70 instances, 20 hosts, 3,000 threads running, and so on. But these kind of systems also inside of your application, these kind of microservices, are calling other microservices that are handling, there are only 2 hosts and 2 instances and running in 300 threads. And you can see that is kind of overwhelming for the system that doesn't have as many resources associated to it. So anytime you are having a many-to-one or many-to-few relationship, you can end up in this situation. So I'm not saying that you should not scale your system. I'm saying that you should think about how much you want to have that many-to-one or many-to-few relationship and when it might break. Other times, the scaling results pattern is resulting when people are creating the shared resource or the commons project that is used commonly by all the microservices. And well, that one is like acting like a bottleneck when you're trying to scale something. And of course, there's another symptom that's of the scaling part, dangerously combining the horizontal and vertical auto-scaling, like not knowing what you're doing and horizontally, vertically scaling your resources, thinking like, hey, something must happen there, and it will serve the user requests. And last but not least, of course, the counterproductive usage of elastic scale patterns or of the predictable demands. So try to, even with your building something with an orchestrator and you're letting the orchestrator do this job, try to think how the relationship between the parts of your system are going to evolve in time, and how you want to keep those harmoniously. Why is it bad to end up with the scale results anti-pattern? Well, because one service can flood another. And request things beyond its capacity, and that's the worst case scenario. And if you're using the shared resources or the commons project, that is a capacity constraint for your system. So as I said earlier, a bottleneck. What solutions are there? Well, first of all, you designed a distributive system. And one thing that is known in the literature about distributive system is there are shared nothing architecture. Getting to a shared nothing architecture is very difficult. So you should try to approximate that one. Of course, there are always trade-offs on doing this, but you can approximate that, and you can, steer towards a shared nothing architecture by continuously improving what you're doing there. So this is something at design level. Another thing you should think about, like having pairs of application that act as a failover for others. So design things in pairs to make sure that when there's going to be a failure somewhere, there's somebody who's going to take an act in case of that failure. What solutions are there for scaling at the Kubernetes level? So one of the options for scaling at Kubernetes level is to use the cluster autoscaler, which is really nice. The cluster autoscaler is actually spawning to you another node, but be aware that this one needs the same resource footprint. So try to provision the nodes of your cluster with a similar resource capacity. Otherwise, you are going to confuse the autoscaler because won't know which pattern to follow. Also, by the way, the autoscaler has its own resource associated to it, and it should have enough, memory and CPU to be able to run and spawn things in your own cluster. And another technique that is very useful for scaling in Kubernetes is using over-provisioning. So over-provisioning technique means to put the so-called pause pods there that have low priority in your node, and to have those as helpers when you're kind of running out of resources on your node. So when you're running out of your resources on your node, Kubernetes is going to evict those pause pods because they have the lowest priority. And your monitoring system can be notified and say, hey, the pause pods are getting evicted, so you might be out of space really soon. So please be aware of this. This is a very useful technique, and you should think about having it in order to, have some buffer space in your cluster node. And last but not least, at the small level, the application level, what you can do is as said earlier, you can define the resources and the limits and make sure that you are using those resource requests close to actual usage. Like as said earlier, do not put more thinking that it should be there in case of need. Always remember that you can scale out with replica sets. You should install the metric server, and you should configure some external metrics in order to have a better monitoring and see what's going on with your system, so you get notified when things are not going as good as you expect, or when there are hypes in the load on your actual applications. And last but not least, to protect your most valuable application pieces with pod disruption budgets. So you make sure that at least a certain amount of pods is available to that. Some takeaways from the current presentation that I would like to leave you with is to avoid deploying things in a specific order when you're thinking of building a cloud-native application that is a distributive system, because you will introduce yourselves some dependency between your applications that they shouldn't exist there. So be brave and go and deploy concurrently your stuff. You should consider setting the memory and the CPU limits in order to reduce the risk of resource contention, and to make sure that you are not getting triggering to the out-of-memory killer and all the other resources from your namespace do not get actually placed in your namespace because you had a deployment not set correctly with the memory and the CPU limits. To utilize, of course, Kubernetes self-healing mechanism is a good thing, but always use those with the retry patterns and circuit breaker patterns also at your application level. So even though that Kubernetes is there to help you and support your application from an infrastructure point of view, do not forget that your application has also some responsibilities to reduce failure for your users. And last but not least, to avoid using both horizontal and vertical pod autoscaler, and to consider installing a metric server and add more custom metrics when you need to fine-tune the horizontal scaling. And this was pretty much it from my side.